Okay. So you should divide by the Q. Should be 1. Okay. Because of the theta 4 and theta 2 equal to theta 3. So this is the one side in relation to the Sn function. Okay. Then he did a further calculation. I don't know whether I should do it. Okay. Maybe it's better to stop here. you need to choose a special way, in such a way that he also shows that a very interesting formula like theta 4 square and theta 4 of x plus y and theta 4 x minus y is equal to theta 3 of x square, theta 3 of y square minus theta 2 of x square, theta 2 of y to square. There are many such formulas. And finally, using this formula, he shows that the addition theory of the theta functions. So namely, what he proved is following. Theta 2, 0, and theta 4 square, and so theta 3, 0, and then take theta 1, x plus y, and here theta 4 of x plus y. Then this can be written in the following way. 1 minus theta 1 x square, theta 4 x square, theta 1 y square, theta 4 y square, and here theta 1 x, theta 4 x. Right? And plus theta 1 y, theta 4 y, and then theta 2 x over theta 4 x, and theta 3 x, and theta 4 x. And this looks like very much about the addition formula for Sn function, where originally obtained by the inverse of the elliptic integrals is given by k square Sn x square Sn y and Sn x Cn x no y dn y plus Sn y Cn x dnx. And using these relations, actually, Jacobi proved that the following important theorem. So actually, our original Sn x is written by this is given by the theta 0 and theta 1 of x over 2k, theta 4 of x to k. So you have to slightly change the variables. So this is actually the u originally. No, not u. So u is here, so the relation k prime of theta 4 of x to k and theta 1 of theta 2 of x to k, and here dnx is given by square root of k. Let's square root of k or k prime. K theta 3 x to k theta 4 of x to k. So it must be k prime. Where what is k? K is given by where 2k is given by pi theta 30 square. Oh, this is easy. Result in vector functions, starting from the theta function. So he can show that using this theta functions and going back in different ways, so finally shows that this function is just inverse of the integrals. So in this way, he gives, in a sense, quite sound foundation of the SN function, because our theta function is now the very good function or the complex numbers. So that everything is defined over here, and x is all complex variables, and this is also complex variables. It's defined. So that you will not constantly extend the inverse function step by step. But this is automatically given. So this gives you some theory. Okay. But somehow, something is lacking, I think. So something lacking is what kind of the function we are considering. So we define that every function as an inverse of the integrals and get some nice properties, W periodic. And also that Jacobi shows that there exists some nice function called theta function, and your elliptic function is defined by the quotient of the two nice functions. But the question is somehow, what kind of function you get? This is a very special class of the function, but we really want to know that more generally, what kind of the function we got it. And this was first done completely different way by Cauchy. And somehow Cauchy was not interested in the elliptic function. Seems he never got about the paper about elliptic functions. But he was really interested in the sort of the integrals. And here are the many papers, sometimes too many, so it's quite difficult to follow carefully. And the most important paper seems the paper for memoir sur l'intégrals défini. So it's a memoir on definite integrals. But actually, this was presented to the Paris Academy, but only published, I think, around 1825. And also, at the same time, 1825, he published a certain note, memoir sur l'intégral défini, the same as Priest's entrée de limit imaginary. Imaginary is, sorry, I'm writing this too bad. And so does the 1825 paper. He announced that he used some imaginary numbers. Okay, so what he did. So Cauchy really wanted to find a good way to calculate the definite integrals. And already in the 19th century, it's Euler and I think sometimes Laplace use some complex numbers to get a special case of the value of definite integrals. Of course, Euler did more. He used complex numbers so that he found that he can introduce the exponential function as complex variables and also logarithm function in complex variables and so on, and also sine function and sine function, and moreover, Ez is related to the cosine z plus I sine. It's quite difficult to say whether he really proved or not, but he used a very strange argument. He used as if that the infinity is a real, is an existent number. Sometimes he uses it, but of course you change very carefully about the limit process. His argument you can always justify this process. Maybe later I'll come back to this problem because we already use in special case this Weyer's formula. But somehow so anyway, that Euler and Laplace found that sometimes if you integrate along the some imaginary directions, you can calculate the definite integrals. And also Cauchy did a similar method. And first observation, Cauchy, I think already at Euler knew that and use it is if you have a nice function of two variables and you first integrate x and dx in the rectangle. Okay, so you can change the integration. First x and dy. For example, f is continuous, there is no problem about this. We can generalize more general function, and that's called the Fellini theorem sometimes. But somehow, he started this. Okay. Now, this is the point. He considers a function of complex variables. Okay? This is a complex value function with complex variables. And he writed this as the real part of this function and imaginary part of these functions. Okay. And then Cauchy remarked was, I don't know. Yeah, Cauchy was a founder of the real analysis, in the rigorous real analysis. He introduced the delta epsilon method. But somehow, his definition of function is very vague. And actually, I think Cauchy thought that the function as a sort of that defined by something, elementary function or something defined by sort of power series, as Euler did. In this case, You can show that.